All right, engineers, so we're going to finish off the last part of the electron transport chain talking about exactly how we're making ATP at this ATP synthase. Or sometimes you even call it complex 5 too, but we're going to call it ATP synthase here. There's so many different proteins that are a part of this ATP synthase. It's actually a beautiful thing. It's almost like a motor, like an engine motor. It's pretty cool. There's a lot of different proteins that are involved in it. Technically, they call this one the C protein. So this part right here is actually made up of like a C component, the C protein. This one right here is actually specifically A. This is your B1, your B2, which are coming all the way down here. And then this protein component right here is actually going to be delta. So this would be your delta. This is actually going to be specifically, this one right here is actually going to be the epsilon. And then this component right here is going to be your gamma. And then these are your alpha, beta, alpha, and it keeps going all the way around, beta, alpha. All right, so what's special about this? Oh, one other thing. They actually divide this into two parts. So that you can divide it from this part here all the way over here. You can divide this into F0, okay? Then you can divide this part over here into F1. And I'll explain why that's significant in a little bit, all right? So now, where do we leave off? What did we say was the significance of all these electrons transporting? It was good to get pumping the protons out from the mitochondrial matrix into the intermembrane space. And what did that do? Remember we left off by saying this established a concentration gradient. Which one's higher in concentration, the intermembrane space or the mitochondrial matrix? And again, don't get confused by -9, -7. This right here, 10 to the -7, is closer to 0. Right? This one's farther away from 0. So this is smaller and this is larger. So the proton concentration out here is going to be greater than the proton concentration over here, which is going to be lower. So the concentration gradient established is going to be moving from high to low. It's going to want to move from the intermembrane space into the mitochondrial matrix. One other thing, I'm going to represent protons with just plus charges because that's all they are. There's a lot of these protons accumulating out here, right? So specifically, as these protons start accumulating, you know protons carry this charge, and whenever they start getting really charged out here, it can develop kind of a depolarization of this membrane. And as this membrane starts getting depolarized, it does something. It starts activating this protein structure, this ATP synthase. Now, what's going to happen is, this A component here of the ATP synthase, it has a tiny little pore. You see that pore right there? That pore is opening up into the intermembrane space. And that pore right there is opening up into the mitochondrial matrix. The protons are going to run down this A protein through this pore and out through the other one. But what are they moving from? They're moving, again, one more time, from high concentration to low concentration. So let's show that here in red. Let's say I take a proton here. This is our proton, and it's moving through this pore and out this pore. And then we just pumped the proton from where? From areas of high concentration to areas of low concentration. Whenever the proton is moving from high concentration to low concentration, it doesn't require energy. It's a passive transport. When you're moving passively from high to low, something really crazy happens. Now the mechanism in here is there's actually a protein here. It's called arginine 210. And I'm going to dumb this mechanism down a little bit because it's not significant that we actually know exactly how it's working. But as the proton's coming in, there's actually two channels. Let's say it comes in through one channel and it meets the arginine 210. Now let's say that here's one channel on this side and there's another channel behind me. Arginine 210 is kind of the one coordinating this. So what happens is the proton's coming at arginine 210. He takes that proton and switches him over and puts him into another channel. But when he puts him into the other channel, he swings back. When he swings back, it rotates this. You see this part right here? It starts rotating this. This is the rotor. Specifically, this part right here is the rotor. And then this black knob part right there, that's the rod. This is actually the rod. And then this part right here is actually going to be the knob, specifically the catalytic knob. And then this whole part here with the A and the B1, B2, and even the delta subunit, this is all part of the stator. What happens is, whenever the arginine 210 is passing the proton from one side to the other side, it creates this little rotation. And this rotation, look what happens here. this C component starts moving. So it moves and does this actual rotation. As it's rotating, so is the rod. And when the rod and the rotor start rotating, it generates this nice little protomotive force, right? So as the protons start accumulating on in this area, they move from high concentration to low concentration. There's this protomotive force that's generated. And from that, what happens is as the protons move from high concentration to low concentration, that ATP synthase absorbs some energy as it moves down its concentration gradient. Specifically, we could say potential energy. As it's absorbing that in the form of potential energy, what it does is it uses that energy from this rotation to do something really special. Let's say I zoom in on one of these knobs. Specifically though, the specific part of this knob should be the beta catalytic subunit. So on here, I'm going to zoom in on one of these beta catalytic subunits and explain to you exactly what's happening. So this is our beta. In this, you're going to have two molecules. One is actually going to be called ADP. So one's called ADP, adenosine diphosphate. In the other part of this pocket, you're going to have an inorganic phosphate. As I told you, the proton's moving from high concentration to low concentration. Arginine 210 is helping in this process. The rotor is rotating. The rod is rotating. It's generating this protomotive force. As the protons move from high concentration to low concentration, this whole ATP synthase absorbs some of that energy as it moves down its concentration gradient. And as it starts rotating, this knob, it's actually rotating also. As it rotates, it does something really cool. It uses that energy from the protons moving down their gradient and takes that inorganic phosphate and the ATP and smushes them together. When it smushes them together, what do you get from that? What will be the overall result of that reaction there? ATP. So out of this reaction, I'm going to get ATP. Now, when I make ATP by this mechanism of moving protons down their concentration gradient, generating this protomotive force, and then I take ADP and inorganic phosphate, and I utilize potential energy from this actual, what is this called? When average proton is actually moving down its concentration gradient. Usually just say it's moving down its concentration gradient. They call this movement of protons from high concentration to low concentration, moving through this ATP synthase, the chemiosmosis. And the chemiosmotic theory, so again, what is it called? It's called chemiosmosis. And this is due to the protons moving from high concentration to low concentration through the ATP synthase. As it does that, the theory of chemiosmosis says that whenever this protomotive force is developed and the potential energy absorbed from this reaction of protons moving down their gradient is established, it generates potential energy that takes the ADP and the inorganic phosphate, fuses them together to make ATP. You know what this process is called? Whenever you do that, do the chemiosmotic theory. This right here, when you make that ATP through this mechanism at the electron transport chain, they call this oxidative phosphorylation. Oxidative phosphorylation. This is much different than the phosphorylation that you actually generate within the Krebs cycle and also within glycolysis. This oxidative phosphorylation generates large amounts of energy as compared to the substrate phosphorylation that's generated from glycolysis and the Krebs cycle. Now, one more thing I want to talk to you about. You know that there's ways that we can actually manipulate this? Because you know all of this is dependent. The whole electron transport chain is coupled with this ATP synthase. So without this ATP synthase actually moving these protons down to generate energy, we would be hopeless. So you know what people have done? They've become very intelligent. And they said, how about I give them a drug? Because I think we can actually help people lose weight. Let's give them a drug. And this drug is going to help them out because what it's going to do is it's going to make a hydrophobic pore in this membrane. I'm going to make this hydrophobic pore in this membrane here. And when it did that, look what happens here. What do you think happens? This is not going to be generating energy. This pore is not generating energy. But again, what's really high out in this area? It's not just here, it's all over this darn thing. There's protons all over this intermembrane space. Because you have to remember, I just zoomed in on one component of that electron transport chain. There's thousands and thousands and thousands of them all across this mitochondria. These protons can now move from where? High concentration to low concentration. But what's the problem with this? Is this step generating any ATP? Is this protons moving from high concentration to low concentration? Is this generating any ATP? No. So it's no longer coupling what? The electron transport chain with the ATP synthase. It uncouples it. If this is not producing, if this protons moving down aren't producing ATP, what will happen to your ATP levels as a result of this situation? This will decrease your ATP levels. If you know anything about what we've talked about, ATP is such an important and potent regulator of glycolysis, the transition step, the Krebs cycle. What will happen if there is decreased ATP or increased ADP? You know what will happen? You'll start driving a lot of glycolytic processes, a lot of transition step reactions, a lot of Krebs cycle activity. What is that doing? That's increasing your metabolic rate, but you're still not making a lot of ATP because you're providing this uncoupling pore. You know what this is going to do? As a result of you not making enough ATP, you're going to generate a lot of heat. Your thermogenic capabilities are going to increase. As a result, this helps with the weight loss process. What is this hydrophobic pore? This hydrophobic pore is actually referred to as 2,4-dinitrophenol. They don't sell this anymore because obviously it's extremely dangerous. I mean, you probably might be able to get it, somewhere. I don't know. But anyway, the whole point here is that it's extremely dangerous because it's uncoupling what? It's uncoupling the electron transport chain with the ATP synthase, and it provides an alternative route for protons to move through, not generating ATP, which increases your metabolic rate, and a lot of, what's the overall result of this then? A lot of heat production. And if there's a lot of heat production, what is that going to do? That's going to help with weight loss, right? But again, it's an extremely dangerous diet pill that they probably shouldn't give or do give anymore. What else is interesting about all of this? Really, really important stuff. I really need to mention this one, guys. You see the cytochrome A plus A3, how it's taking these electrons from the iron 2 plus and going to iron 3 plus. But when it loses those electrons, who does it give it to? It gives it to oxygen. And then oxygen is going to do what? It's going to use that oxygen to make water. You know what else can really, really destroy this? All right. It's an unfortunate thing. You might have heard of cyanide. So cyanide poisoning, for some odd reason, if you have cyanide poisoning, you know what it's going to do? It's going to inhibit this step. Can you transfer the electrons from the actual cytochrome A plus A3 or cytochrome oxidase onto the oxygen? No. And that is going to destroy a lot of problems, right? It's going to cause a lot of, what can this cause if you have cyanide poisoning? Specifically physiologically. This can cause what's called hypoxic hypoxia. So in other words, you have plentiful amounts of oxygen, but you just can't utilize that oxygen. Okay, and it exhibits in the form of hypoxia. You know another dangerous one? Carbon monoxide. CO, carbon monoxide. It can also inhibit this step. If carbon monoxide is inhibiting this step, can you utilize any of the oxygen also? No. So carbon monoxide is also dangerous at this point too. And this can actually lead to hypoxemic hypoxia. But you've probably also heard of carbon monoxide binding where? Onto the iron-containing heme group in hemoglobin. Because this is also a heme molecule. So it also will bind there. Okay. If that's happening, it's obviously going to cause a lot of problems within this electron transport chain. And there's many other drugs that you could even target. Going from cytochrome B to cytochrome C, you can also use another molecule called antimycin A. I think it was before an antibiotic, but again, you're probably not going to want to use that anymore because obviously it can mess up this whole process too. And there's even other molecules like rotenone, many, many different things. But one more that I want to mention. Babies are really, really interesting. Babies have what's called brown adipose tissue because us adults don't have brown adipose tissue. Whenever you're a baby, most mammals, especially babies whenever they're born, they have what's called brown adipose tissue. The only reason it's brown is because it has a lot of mitochondria. What's special about the brown adipose tissue is that it helps to produce a lot of heat because it uncouples. It does kind of like this mechanism here. It uncouples the actual electron transport chain from the ATP synthase. But how do they do that? How exactly are babies doing this? Babies, or even in bears, they're actually coming out of hibernation. They also can do this too. Look what happens here. they can uncouple this actual process. And what they actually do is they produce a molecule called thermogenin. And what this thermogenin does is it kind of acts just like this DMP, but only specifically in brown adipose tissue. And what happens is it creates a pore inside of the membrane. If it creates a pore inside of the membrane, what is that going to do? That's going to uncouple. It's going to do the exact same thing you saw before. As this uncouples, what's going to happen to these protons? They're going to move down their concentration gradient, but no ATP is going to be made. If very little ATP is going to be made, what's going to happen as a result? Same thing with the DMP. You're going to produce a lot of heat. Why is this important? Because it's important for the bears whenever they're in that hibernation period to be able to stay warm, right? Why else? Because the babies have to be able to maintain their actual warmth also. And again, this is only happening in brown adipose tissue. And this is due to a chemical called thermogenin that their body is making. Specifically, again, in mammals, like bears or, even babies. All right, one last one, guys, and we're done. You can also inhibit ATP synthesis directly at this point, too. You can give a drug right here that can literally bind into this subunit right here, this F0. He can literally bind in here. What is this drug that can bind into this area right here? This drug is specifically called oligomycin. And oligomycin can inhibit the, what is this unit right here called? F0 subunit. All right, so oligomycin can also inhibit the F0 subunit of this specific ATP synthase. And you even have another drug that can inhibit F1. If you're curious, it's also called rotenone. And it can inhibit the F1 subunit from synthesizing ATP. So there is mechanisms that you can directly inhibit the ATP formation, or there's mechanism that you can actually indirectly inhibit the ATP formation. And then there's ways that you can also alter. There's also translocases that are moving the ATP and ADP in and out of the mitochondria. You can also give them drugs that target that, called a tractyloside. All right. What we're going to do now is we're going to tally up everything. Let's go ahead and tally up all of the actual energy that's going to be produced from the electron transport chain, considering all of the reactions that we've done so far, starting with glycolysis all the way to this point. Okay, so from glycolysis, what were you actually generating out of this? Well, you were generating 2 ATP, right? From what? From the, I'm going to put SP, substrate level phosphorylation. You were also generating 2 NADHs from glycolysis, right? The transition step, you were generating 2 NADHs. And then the Krebs cycle, you were generating 6 NADHs and 2 FADH₂s and also 2 ATP via substrate phosphorylation. Now, I need to explain one more thing, and then we're going to go ahead and tally all this up. NADH, how many protons did it pump out again, guys? If you guys remember, let's follow it through. It pumped out 1 here at complex 1. But follow his electrons. Where did those electrons go? Okay, it went to Q. All right, okay, it went to this Q. Okay, it went to this guy, 3. And what did 3 do? He pumped a proton out. Okay, that's 2 protons. Okay, follow the electrons again, guys. Go from 3, okay, goes to C. Okay, goes to this isotonic oxidase. And then what? Oh, pumped another proton out. That's 3 protons from 1 NADH. Okay, and then I know that whenever 1 proton that comes down gives me 1 ATP. Okay. What about this guy? FADH₂. He was dropping his electrons off onto 2. Was he pumping a proton out? No. Okay, where else? Right there, 3. Pumps a proton out. He passes the electrons on again. 4. Pumps a proton out. How many protons is that? That's 2 protons. And then if you remember, for every 1 proton, you generate 1 ATP. What can be said of that now? For 1 NADH, I get 3 ATP because I pumped out 3 protons. For 1 FADH₂, I get 2 ATP because it only pumps out 2 protons. All right, now we're on a roll. So if this is the case, how many ATP is 2 NADH giving you? 3 times 2, 6 ATP. Same thing for this one, 6 ATP. 6 times 3 is 18 ATP. 2 FADH₂s, it's 2 times 2. That's going to give you 4 ATP. And then the 2 ATP by substrate, phosphorylation, this will give me another 2 ATP. Don't know why I wrote that twice, but you guys get the point. And I'll just do this for the heck of it, 2 ATP. If we add 2 ATP plus 6 ATP plus 6 ATP plus 18 plus 4 plus 2, what is that going to give me as a grand total? My grand total is going to be a total of 38 ATP. Now, if I'm making 38 ATP, this is taking into consideration all of the actual ATP from both aerobic and anaerobic cellular respiration. All right, guys, we did a lot of information in this video and throughout the series of these videos. I hope all of them made sense. I hope you guys really enjoyed it. If you did, hit that like button, subscribe, hit the, put some comments down there. We really look forward to hearing from you guys. All right, until next time, Ninja Nerds.